Hello, so this is the video for the final project for the computer vision course. My project consisted in entering a Kaggle competition. This was the Google research identified contrails to reduce global warming competition. This one consisted of training a machine learning model to identify contrails in satellite images and help prevent their formation. So for context, contrails are condensation trails, which are long, thin ice crystal clouds that form in an aircraft engine. These contrails can linger and grow for several hours, merging into cloud formations, making them very difficult to detect and contributing to global warming. So the reason why it is important to detect them is to help researchers improve the accuracy of their contrail models that predict when contrails will form and how much warming they will cause. As for the dataset provided by the challenge consisted of geostationary satellite images retrieved from the GOES-16 advanced baseline imager. The trained data consists of multiple sequences of images with one main labeled image. So because as contrails are easier to identify with temporal context, the challenge provides a sequence of images at 10-minute intervals, 4 before the labeled image and 3 after. For each of these sequences, there are 9 different folders that represent bands that are the infrared channels at different wavelengths and are converted to brightness temperatures. So each record ID also holds a human pixel mask, which is an array that is the per pixel binary ground truth for the contrail detection. So basically, in which pixels there are contrails. The objective of the competition was to apply, of their solution was to apply image segmentation to identify which pixels have contrails. So the proposed solution was to implement a model with image segmentation with temporal context to identify the pixels that contain contrails. So now for the code, the solution was implemented in a Kaggle notebook because it is required for the submission for the competition. So first, to access the data, you first have to accept the rules of the competition, and after that you can add the data in the input section, searching for the name of the competition. Then you have to select the accelerator, the GPU D4x2, and then, here is the context and the information about the data, and then we just run the code. We see here we're running each cell, the reproducibility, just seed everything to get the same results. Here is the information about the color scheme of the images. So we need to represent the images in an RGB format using the satellite bands. So instead of using all 9 bands, we only use 3 of them using the ash color scheme. Then we can see a small visualization to see how the images were represented and how you can see them. After that, we have to modify those images to get them in the right format for the model. And the solution consisted of a 3D UNet model that is widely used for 3D image segmentation that consists of 3D convolutional layers and a symmetrical encoder-decoder structure with skip connections to segment volumetric data. So in this project, the 3D data is provided by the temporal information, basically. So instead of just doing the 3D convolutions in the bottleneck, I used of the unit, I used a convolutional LSTM to process temporal context. So we use this to model temporal evolution of contrail formation, so the model learns how features evolve over time. The loss function used was a combination of binary cross entropy and dice loss. Then 50% each, basically. And here we have the code for for preparing the data and the training. The model was trained for 15 epochs with the Kaggle GPU, the T4 times 2. And here we leave it running, and the training lasted approximately 6 hours. After training, after the 6 hours, we get the model with the best global dice of 0.5475, and then to check the model, I made some predictions to some of the validation images. One image that does not have contrails, and one with contrails, to see how the model performed. Here we can see the ground truth and the model prediction, the comparison of the two, where the white pixels are contrails identified. After this part, we have to, the last thing is to make the predictions on the competition test. So we need to encode the results into the necessary format and create the necessary submission CSV that we can see here. And the last thing to do is to save this version, which lasted approximately 6 hours as well. So after saving the training notebook, we're going to get the same notebook with the same code, but with the results and the model already run. So from here, we have to go to the output, and we see the best model output file, where we have the weights of the model that performed the best. And we have to create a data set of this to be able to use in a future notebook for the submission, the official submission of the official submission from the competition. So in the submission notebook, it's pretty similar, but we add to the input the competition data and the weights that we saved as a data set. We choose the GPU and we turn the internet off. This is basically necessary for the competition because it has as requirement to have a runtime less than 9 hours. So it's better to submit the notebook that does not have the training in it. So we run the same cells, and basically the difference is that instead of training it, we upload the weights, and we do the same encoding to get the submission file CSV as we saw before. And we save that version. That takes some time as well. After saving the version, we go to the view section of the notebook, where we have the whole code already run with the outputs. So we go to the output section, we go to the submission file, the .csv, and we click submit to the competition. For the competition, it's evaluated on the global dice coefficient. The dice coefficient can be used to compare the pixel-wise agreement between the predicted segmentation and the corresponding ground truth. So after the submission is uploaded successfully, the competition provides the private score and public score, which are very close to the ones I got in the validation, which is 0.5473. And the last thing I want to show is the GitHub that has the weekly logs, the README file. It has the instructions on how to access the data, the dependencies, description of the solution, and the links for the Kaggle notebook, both for training and submission. And we have the notebooks and the results, which I want to show So basically, in the results, we have the comparison of the different models I tested. I tested different versions of the 3D unit, some with that data augmentation, some with DIT, attention gates. And basically, I trained the model in the best performed, the one that best performed in the 8 epochs that I evaluated all of them. That was the 3D unit with convolutional LSTM. In the results also there is the images of how the model performs of how the image segmentation works, and the competition score. Some challenges for the project were the learning curve for learning to code with PyTorch. I don't come from a coding background, so it took some time. The other one was the training times and the GPU access that, well, it has you're allowed a limited time per week in Kaggle. And some ways to improve the model to get better results, researching from other people that participate in the competition. Someone found that the masks, the labels, were shifted by 0.5 pixels, which made the data augmentation, like flips and rotation, make hurt the model. That could be the reason why when I applied that augmentation, I got worse results. So a way to improve the solution would be to pre-process the masks and to apply data augmentation. Also, some people used a 2.5 unit instead of a 3D unit, which seems to give higher performance.